Welcome, and thank you for standing by. Today's conference is being recorded for replay. If you have any objections, you may disconnect at this time. All participants are on a listen-only mode until the question-and-answer session of the conference. During that time, if you would like to ask a question, please press star then 1 and clearly record your name for question introduction. I would now like to turn the call over to your host, Ms. Loretta Jackson Brown. You may begin. Thank you, ma'am.
Thank you, Nichelle. Good afternoon. I'm Loretta Jackson Brown, and I'm representing the Clinician Outreach and Communication Activities, COCA, with the Emergency Communication System at the Centers for Disease Control and Prevention. I'm delighted to welcome you to today's COCA webinar, Emerging and Exotic Diseases of Food Animals Threaten Global Food Security. You may participate in today's presentation by audio only, via webinar, or you may download the slides if you are unable to access the webinar. The PowerPoint slide set and the webinar link can be found on our COCA website at emergency.cdc.gov/COCA. Click on COCA Calls Webinars and follow the link for today's call. Free continuing education is available for today's COCA webinar. Information on how to obtain credit will be given at the end of today's call. CDC, our planners, presenters, and their spouses, partners wish to disclose they have no financial interest or other relationship with the manufacturers of commercial products, suppliers of commercial services, or commercial supporters. Planners have reviewed content to ensure there is no bias. This presentation will not include any discussion of the unlabeled use of a product or products under investigational use. At the conclusion of today's session, the participant will be able to review recent examples of emerging diseases of food animals, discuss reasons for emergence and dissemination of diseases of food animals, describe challenges for control of zoonotic and non-zoonotic food animal diseases, and suggest infrastructure changes needed to improve prevention and control of food animal diseases. At the end of the presentation, you will have the opportunity to ask the presenter questions. On the phone, dialing *1 will put you in the queue for questions. You may submit questions through the webinar system at any time during the presentation by selecting the Q&A tab at the top of the webinar screen and typing in your question. Today's presenter is Dr. James Roth. Dr. Roth is the Clarence Hartley Kowal Distinguished Professor in Veterinary Medicine and Director, Center for Food Security and Public Health with the College of Veterinary Medicine at Iowa State University. He is a board-certified microbiologist, a noted disease researcher, and a respected instructor. Dr. Roth has been the recipient of many awards, including the Distinguished Veterinary Microbiologist Award from the American College of Veterinary Microbiologists, the Public Service Award from the American Veterinary Medical Association, and the USDA APHIS Administrator's Award for Lifetime Achievement in Animal Health. He has testified before Congress on biosecurity preparedness and efforts to address bioterrorism and agroterrorism. Dr. Roth served on the National Science Advisory Board for Biosecurity since its inception in 2005 until 2014. Again, the PowerPoint slide set and webinar link are available from our COCA webpage at emergency.cdc.gov/COCA. At this time, please welcome Dr. Roth.
Thank you, Loretta, and thank you for the opportunity to give this presentation. As I'm sure the audience is aware, we're living in a time of new emerging diseases in both people and animals. I'm going to quickly review some of those diseases and highlight some of the diseases of animals and the challenges for their control. First of all, a review of the emerging diseases, zoonotic diseases of people in the last 35 years. If we look at this list, in 1981, HIV/AIDS was first noticed in the U.S. or detected in the U.S. 1982, the E. coli 0157H7 was described, and Lyme disease. Bovine spongiform encephalopathy was detected in the United Kingdom, also known as mad cow disease, as a brand new, never seen before prion disease. And that was in 1986, and it wasn't until 1996 that it was realized that that was a zoonotic disease, when variant Creutzfeldt-Jakob disease was described in the United Kingdom. The Hendra virus emerged in Australia. It's a Nipahvirus that is in fruit bats, carried by fruit bats. It was transmitted to horses and then to people. Very few cases in people, fortunately, but they did have high mortality rates. Avian influenza in 1997, the H5N1, was first detected in humans. Prior to 1997, high-path avian influenza was not thought to be an important zoonotic disease. And now I think we're all aware that it is one of the most important zoonotic diseases in the world because it's changed to be able to be transmitted to humans, and this particular strain has a fairly high fatality rate. The Nipahvirus in Malaysia, another virus harbored by fruit bats, was transmitted to pigs and then into people with a fairly high mortality rate. I'm going to spend a little bit of time on that one as an example. West Nile virus, which entered the United States in 1999 and then, as you all know, spread throughout most of this hemisphere. SARS in China, and then it spread to a few other countries before it was brought under control. 2003, there was monkeypox, SARS went globally, and we had the first case of bovine spongiform encephalopathy in the U.S. And in 2004, H5N1 reemerged in Asia and killed hundreds of millions of chickens with hundreds of human cases. 2005, it spread to Europe and Africa. In 2009, the pandemic H1N1 influenza occurred. It was an influenza virus that contained some genes from swine influenza virus. 2007, the variant H3N2 influenza virus in the U.S. Middle East respiratory syndrome in 2012, and then a new avian influenza H7N9 in China in 2013. This one is unusual because it's low pathogenic in poultry, so it's easy to miss it in poultry, but it has produces fairly severe disease and mortality in humans. So in the last 35 years, we've seen a number of very important diseases emerge. You can imagine what life would be like without those diseases now. They've changed the world. We have to assume in the next 35 years we may get a similar list of new diseases that are zoonotic, transmitted from people or animals to people, and some from people to animals. And we're also seeing new emerging diseases in domesticated animals. Today we're focusing on food animals, so I'm going to focus on ruminants, swine, poultry, and aquatic animals are a very important food-producing species, and we'll go through some of these examples. So what are the factors contributing to the continuing emergence and reemergence of diseases in both people and animals? We'll just review these very quickly. Overpopulation, the huge increase in human population, is the fundamental driver of the emergence of these diseases, and we'll look at that a little more closely. Intensive animal agriculture and increased backyard animal production are both increasing because of the need to feed the increasing human population. Each of these has advantages and disadvantages. Intensive animal agriculture produces a very high-quality product at a low cost, and it produces high volumes of animal-based food. It typically has very good biosecurity. However, if the animals get sick in these very large units, as we're now seeing with avian influenza, there are an awful lot of animals that get sick and need to be disposed of typically. And the more that a virus mutates or replicates, the more chances it has to mutate and change. Backyard animal production is efficient because they often use waste food for the animals. However, the people and animals typically live in close proximity, so zoonotic diseases can be transmitted to people easily. And typically these animals don't have any veterinary care or vaccinations. The wildlife, domestic animal, human interactions are increasing with the increasing population of people and domestic animals, and this provides opportunities for interspecies transfer of pathogens, and that's how many new diseases arise, is a virus especially that's capable of jumping from one species to another. Environmental degradation contributes to the emergence of new diseases. Climate change and globalization all contribute to the emergence of new diseases. As I mentioned, the driving force behind the emergence of diseases is the growing human population. This graph shows the population from approximately 1400 through the present time and projected to 2050. In the 50-year period between 1960 and 2010, the population more than doubled. There were about 3 billion people in 1960. It increased by about 3.9 billion people by 2010. And it's projected to slow a little bit, but to have another 2.6 billion people in the world by 2050. You have to ask yourself, how long do you think this logarithmic growth in the human population can continue? And if it's not going to continue to grow, what will be the forces that cause it to level off or decline in the future? And because of the increasing human population in the last 50 years, there's been a need for increasing food production. This graph shows the world meat and egg production in 1962, which are the small icons for poultry meat, eggs, beef, and pork. And 50 years later, the increase that we've seen. So there's been more than a doubling of the production of poultry meat, eggs, beef, and pork to feed the increasing human population. And that increasing animal population leads to opportunities for the emergence of new diseases. And in spite of all of that increased food production, there are still a lot of undernourished people in the world. In 2012, the estimate was that there were 868 million undernourished people. Just today, I saw a headline that number is now down to under 800 million, so progress is being made. And even in the U.S., the USDA estimates there are 49 million people in the U.S. that live in food-insecure households, including 16.7 million children and 14% of all adults. Now, that's very different from being undernourished as the figure is for the rest of the world. Food insecure means that at some point during the month they don't have enough resources to buy the food required. The FAO projects that food production will need to increase by 70% by 2050 to feed the projected 9 billion people. And any changes we consider in making in how food is produced, both grain and animal-based food, have to be made very carefully, because if we make changes that increase the cost of food, much of the world spends a very large percentage of their income on food. In the United States, it's approximately 6.6% of income spent on food. Of course, there are many families where it's much higher than that. And in the rest of the world, it increases up to the example in Pakistan, with 47.7% of income is spent on food. If changes are made that increase the cost of food, it can have severe consequences for people that are struggling to purchase food. So that means by 2050, if we're going to have the same relative diet for the same number of people, these figures have to increase by another 70%, and grain production has to increase by 70% with the same amount of arable land to produce all of that food. So I'll review some of the emerging diseases of food-producing animals quickly and use a few I'll focus on with a little more detail. Swine have had some of the most interesting and biggest emerging diseases, greatest impact. Porcine reproductive and respiratory syndrome virus emerged in the late 1980s and quickly spread to most of the world. It's still the #1 disease limiting the efficiency of pork production in developed countries like the U.S. There is a vaccine, but vaccines aren't as effective as everyone would like them to be for this particular disease. Porcine circovirus-associated diseases emerged in the late 1990s, caused a lot of illness and economic loss to the swine industry until a vaccine was made. And fortunately, this vaccine is highly effective and is a very good way to control this disease. So they continue to vaccinate for that. Foot and mouth disease, African swine fever, and classical swine fever are well-known diseases around the world. We don't have them in North America, and if they came into our pig population in North America or other developed countries that don't currently have the disease, they would be devastating to the production of pork. We'll come back to that a little bit. Swine influenza, much like human influenza, is very difficult to control with vaccines because the virus drifts and shifts, so it's very hard to keep up with the virus with the current vaccines available, so it continues to be a problem. And there is always concern of transmission of influenza viruses from pigs to people and from people to pigs. Nipahvirus is a very interesting Paramyxovirus that I mentioned. It emerged from fruit bats into pigs and then into people in Malaysia, and I'll spend a little more time on that one. Meningococcal is another paramyxovirus that's carried by fruit bats. There's only been one instance of an outbreak of meningococcal. In Australia, it was transmitted to pigs from fruit bats and then to people. Fortunately, there are only 2 people that developed influenza-like illness, so it wasn't as serious as Nipah. In 2008, pigs in the Philippines were discovered to be carrying the resistant Ebola virus. This Ebola virus is not pathogenic, or perhaps low pathogenic for people and for pigs, so no clinical signs. After resistant Ebola virus was discovered in pigs in Philippines and then later China, researchers in Canada infected pigs with the Zaire Ebola virus, which is the virus that recently and still is a problem in West Africa. And they found that pigs do become infected with Zaire Ebola virus. In young pigs, it produces a respiratory disease that looks much like any other respiratory disease in young pigs. Those pigs were capable of transmitting Zaire Ebola virus to primates in the same airspace, and the primates became very ill and died. So pigs are a potential vector of Zaire Ebola, although it's never been observed in nature that pigs have been infected with Zaire Ebola virus. And then porcine enteric coronaviruses. We've had 3 new porcine enteric coronaviruses introduced into the U.S. that are identical to viruses in China, so they apparently came from China in the last 2 years. The commercial swine industry in the U.S. has very good biosecurity, or we thought they had very good biosecurity when the porcine epidemic diarrhea virus, one of those coronaviruses, was introduced in April of 2013. It was introduced into the U.S. and discovered after it had been here apparently for 2 or 3 weeks. And in spite of the best biosecurity and increasing biosecurity, the swine industry was not able to stop it from spreading. And by a year later, March 2014, it had spread to all of the swine-intensive states and is estimated to have killed 8 million baby piglets, approximately 10% of the swine population. It causes a very severe diarrhea and vomiting, and the baby pigs die from dehydration fairly quickly. This shows the epidemic curve of porcine epidemic diarrhea virus. It was worse during the winter apparently because the virus is more stable in the environment. The number of cases reported is lower, but it is still persisting, and it's not likely to go away anytime soon. Vaccines are under development for that particular disease. The other swine disease that I want to spend a little time on is the Nipahvirus. The Nipahvirus outbreak, which occurred in Malaysia, many of you may be familiar with that. In 1998 and 1999 in Malaysia, a new respiratory and neurologic syndrome was reported in swine, and it was observed that people working closely with swine were developing encephalitis. And before it was over, there were more than 250 human cases of encephalitis with more than 100 deaths. This was initially mistaken for Japanese encephalitis, which is endemic in that part of the world. Japanese encephalitis causes encephalitis in pigs and in people. They initiated a mosquito control program to control Japanese encephalitis, but Nipahvirus is not transmitted by mosquitoes, so that didn't help. They eventually discovered a new Paramyxovirus, which was causing the disease. This Paramyxovirus is carried by flying foxes or fruit bats, and this is a picture of a fruit bat. They're about a foot long. They carry the virus, but do not become ill. They're inapparent carriers. And the virus is shed in the urine and in saliva. So when these fruit bats eat fruit, the partially eaten fruit still has saliva, which can have virus in it. And these are migratory over a large part of that part of the world. And in serosurveys, 10 to 15% of the fruit bats are seropositive for this family, the Nipahvirus family. This is a picture of where apparently the first case emerged of the Nipahvirus. This is an example of intensive animal agriculture encroaching into an area that did not have extensive pig production previously. On this farm, there were about 20,000 pigs in these shelters. This is a roof with open sides. And they also raised durian trees, fruit trees. And this attracted large numbers of fruit bats. And a very rare event occurred, which was the Nipahvirus was transmitted from fruit bats into pigs, and then it was easily transmitted from pig to pig. So there was high morbidity in the pigs of mostly respiratory syndrome with some encephalitis. And then pig workers started to come down with encephalitis. Before it was discovered what was going on and the officials were able to get it under control, some of the small farmers realized that there was a problem with their pigs, and they sold their pigs cheaply, and that spread the disease to other parts of the Malaysian peninsula. The virus was isolated by a pathologist in Malaysia who was not able to identify the virus. He brought the virus to the U.S., and the CDC was able to discover that it was a previously unknown Paramyxovirus. So the CDC, within a very few days, sent teams to Malaysia to help control the virus, and Australia also sent teams to Malaysia. These are a couple of Australian veterinarians conducting a necropsy on a pig, wearing their personal protective equipment. You can see the kind of pig housing that these animals were in. They very quickly developed a diagnostic test and an eradication program. The virus was first isolated in March of 1999. There's a very quick national response with international assistance, and they ended up culling or killing 1.1 million pigs in Malaysia out of a total of 2.4 million, so nearly half the pigs in Malaysia. And that was effective in stopping the disease because it was transmitted pig to pig. It was very little evidence of human-to-human transmission at that time. And there haven't been any new cases in Malaysia since 1999, even though the fruit bats are still carrying the virus. The fruit bats that are known to carry the Nipahviruses, which is the Hendra virus that occurred in Australia in horses and people, and the Nipahvirus, which occurred in Malaysia, and also has occurred in Bangladesh and India. The Nipahvirus cases in Bangladesh and India are direct transmission, apparently, from the fruit bats to people, because there are very few pigs in Bangladesh, which is a Muslim country. The epidemiology indicates that that virus is shed into date palm juice, and that the local people drink the date palm juice and pick up the Nipahvirus infection. And almost every year there are small outbreaks of Nipahvirus. These bats have a fairly wide range, and the Nipahvirus has been found in bats as far away as West Africa and Madagascar and much of Southeast Asia. So we know that the virus is in the bats, but it's only jumped into pigs once, and a few times into people with some human-to-human transmission, but not a very high incidence. And it's fortunate that that virus emerged in Malaysia, which is, again, a predominantly Muslim country that don't eat pork, but the Indian and Chinese minorities do eat pork. So they only had 2.4 million pigs in Malaysia, and it's a developed country with a very well-developed veterinary infrastructure. So they were able to very quickly stamp out the virus. If that virus emerges in other countries in Southeast Asia where we know the fruit bats are, such as Cambodia with 21 million pigs, Vietnam with 27 million pigs, Thailand, Myanmar, that have extensive backyard production with close contact of pigs and people, it would be very difficult to control that virus if it emerges in pigs again and is easily transmitted pig to pig and from pig to people. Pork is a major source of protein in that part of the world, and if Nipahvirus became established, they would not be able to raise pork, probably. Another very important source of animal-based protein is aquaculture, and aquaculture has really increased in recent years. And this is one estimate of the amount of farm fish produced in the world compared to the amount of beef. And this estimate indicates that the tons of farmed fish now exceed the tons of beef produced in the world. So there's been a very rapid increase. So intensive aquaculture has grown rapidly. It's the fastest growing area of animal protein production. It's estimated that about half of the global aquatic food supply is now from aquaculture rather than wild-caught animals. And in China, 90% of aquatic animal food comes from aquaculture. And this includes fin fish, such as catfish, salmon, trout, tilapia, crustaceans, such as shrimp, lobster, crabs, and mollusks, such as clams and mussels. Intensive aquaculture can reduce the pressure on wild fishery stocks, which have been somewhat depleted of food for human consumption, fish for human consumption. However, some of these aquatic animals, such as salmon, are carnivores, and the need to feed these salmon in these very large operations, so they catch wild fish from the sea and process them into salmon food, and that there's concern that that will deplete those wild fish that are used to feed the farm fish. And with high stocking densities in aquatic animals, just as in other food animals, contagious diseases can be a problem if they get into those densely stocked facilities. Especially in salmon that are raised in large nets in the ocean, the contagious diseases then can spread from the salmon to the wild fish. There have been major problems with sea lice, which is a parasite that can increase in number in the large salmon fisheries and then spread to the wild fish. Infectious salmon anemia has been a big problem. In Chile, they developed a very large aquatic salmon industry that was quite successful until infectious salmon anemia came in and decimated that industry. And now they're having to rebuild the industry, paying close attention to biosecurity to try and control that disease. And in shrimp production, white spot disease has been a real limiting factor in shrimp production. And that brings us into poultry. And in poultry, high pathogenicity avian influenza is a major factor limiting poultry production. And as I'm sure you're aware, we're having a catastrophic outbreak of high path AI in the Midwest currently. So a little history on avian influenza. In 2004 and 2005, H5N1 emerged in Asia and killed millions of poultry and is zoonotic and was transmitted to people with hundreds of human cases and a fairly high mortality rate. When that occurred, there was great concern that that virus would spread through migrating waterfowl from flyways in Europe and Asia to the Western Hemisphere. So extensive surveillance programs were set up in North America to provide early detection for H5N1 should it occur, should it migrate with the migrating waterfowl. And 10 years later, that has never occurred. That virus has never jumped into the Western Hemisphere. However, a new strain of H5 avian influenza was detected in Canada and the U.S. in the fall of 2014. This is a totally different H5. It's not zoonotic like the H5N1 is, but it seems to be more easily transmitted. It's still highly pathogenic for poultry with very high mortality rates in chickens and turkeys. So in the fall of last year, or actually the original H5N8 outbreak occurred in January through April mostly in South Korea and Japan. After 5 months, there were no reported cases. So at the end of the spring, when the warm weather arrived, the H5N8 outbreak ended. And after they were 5 months with no reported cases, because as influenza tends to do, it went away in the hot months. The H5N8 was detected again in September in South Korea and in November in Japan. Also in November, when it was detected as a reoccurrence in Japan, the H5N8 was detected in Western Europe. And by mid-December, the H5N8 was isolated in Germany, Netherlands, United Kingdom, and Italy. So it spread pretty well throughout Europe. In November, again, of last year, the first detection was H5N2 in British Columbia on November 30th. December 10th, the same H5N8 virus was detected in Washington State. And then an H5N1 was detected on December 29th in Washington. This H5N1 is different from the H5N1 in Asia. This one is, there have been no human cases with any of these H5s. So this H5N8 has been referred to as the Intercontinental avian influenza because it spread from Asia to Europe and the U.S. And reappeared in November in all 3 locations. So the Eurasian H5N8 was most likely carried to Alaska with the migrating waterfowl And in Alaska, the Pacific American flyaway birds mingle with the Eurasian birds in Alaska. Apparently, the H5N1 from 10 years ago did not do this because apparently the waterfowl were weakened enough if they had that virus they couldn't make the migration. But the H5N8 was able to migrate with the waterfowl and find its way to this hemisphere. Then the Eurasian H5N8 underwent gene reassortment with low pathogenicity avian influenza strains endemic to North American wild birds. So a wild bird was co-infected with the H5N8 and a low pathogenic influenza, enabling the 8 gene segments to be mixed and matched in new combinations. And that's how the H5N1 and H5N2 emerged in North America. And these are referred to as the Eurasian and American strains of influenza. This is a map of the U.S., obviously, and it was made on May 13th. This is updated weekly, but this is the most recent at the time I submitted my slides. The first cases were found in the Pacific flyway and predominantly in wild birds, and you see that the cases were scattered over that part of the U.S., as you would expect for cases that are predominantly in wild birds and backyard flocks. When the cases appeared in the Midwest, they began appearing in the concentrated poultry regions and are much more concentrated in a smaller area. This shows the epidemic curve from December 8th through May 17th. In the western U.S., in the Pacific flyway, most of the cases were in wild birds. And then it stopped occurring in the wild birds and in that part of the world predominantly by the end of January. Through February, there were a few cases reported. The first commercial flock was reported in Minnesota on the week of February 23rd. There were a few more cases over the next weeks. And then it began to explode in the commercial birds, predominantly turkeys in Minnesota. The first detection of an Iowa flock was in April 13th, about 6 weeks ago. And then we began to see a lot of cases, and these are predominantly in large egg-laying facilities, but also in some turkey facilities. It seems to be slowing down. Everyone is expecting and hoping that this will stop with the warm weather. But just in the past week, there have been at least 10 new cases in Minnesota and some in Iowa. So it still hasn't stopped. Everyone is hoping it will slow down soon. There's great concern that if it goes away in the summer, as it should, that it may come back in the fall, and we need to be prepared. This shows the data as of May 18th for Iowa from the Iowa Department of Ag website. So in Iowa, we've had over 25 million poultry affected, 23 million layers approximately, and most of these are in battery cages, so they're hens in cages, which greatly complicates the depopulation of those cages. The largest facility had 5.8 million birds in one group of houses on one facility, all of which had to be destroyed. And I think there were 7 facilities with over 1 million birds each. And then the pullets that are used to repopulate those facilities, turkeys, a hatchery, very few backyard chickens. And this isn't what I would have expected or many people would have expected if the virus is being spread by migrating waterfowl. Initially, I think there's no doubt that the virus got here through migrating waterfowl on the western U.S. I don't know if we know how it got to the Midwest or how it is spreading between these very large units. There are a lot of people working hard to figure out what went wrong with the biosecurity and what more biosecurity is needed to to prevent this from reoccurring and to get this outbreak stopped. Then for ruminants, there are a number of emerging diseases. Foot and mouth disease, as I mentioned, is endemic in a lot of the world, and I want to spend some time on that one. Rift Valley fever was confined to sub-Saharan Africa for many years. There are periodic outbreaks in ruminants in sub-Saharan Africa. It's mosquito transmitted, and then when there are outbreaks in the ruminants, then it's transmitted to people, and there are human cases. And it had been confined to sub-Saharan Africa until about the year 2000, when it spread to Egypt and then Saudi Arabia and Yemen. So this seems to be on the move. Brucellosis has been a serious disease of ruminants and of people for decades. A lot of efforts to control brucellosis. The U.S. has it primarily under control. Most developed countries do. But there are large parts of the world that don't have it under control, especially where people live in close association with small ruminants. Brucella melitensis is a severe problem in those areas. And then the prion diseases, I mentioned BSE, mad cow disease, which has caused severe problems in the cattle industry and has caused a lot of changes in trade in animals and in how we feed animals. With the ban on ruminant products going into ruminant feed, that's brought it under control, but it needs to be constantly monitored. Blue tongue is a virus disease of ruminants that was rare in Europe until about 1998. The culicoides vectors of this virus apparently have become more adapted to the European climate, potentially aided by climate change. A new strain of blue tongue was carried into Europe, and now they have to vaccinate for that. Tuberculosis in cattle was well controlled in the U.S. and still is well controlled. But there have been problems with brucellosis in the dairy herd in Michigan area being transmitted into wild deer, and then the deer transmitting it back into dairy, so that's a struggle once it gets into the wild deer to get that under control. Schmallenberg is a brand new virus that emerged in Europe, also carried by the culicoides vector. It first emerged, I think, 3 or 4 years ago, causes reproductive problems in ruminants with fetal malformations and stillborn animals. There is a vaccine for that that's bringing that under control. Foot and mouth disease is probably the greatest threat to food production, especially in North America and those areas that are free of foot and mouth disease. It's the most contagious disease of animals, viral disease that only affects cloven-hoofed animals, pigs and cattle, other ruminants, wild animals. It's the major animal disease preventing trade in animals and animal products around the world. The mortality is generally low in adult animals, but the morbidity is high. So nearly all of the animals get sick. Most of the adult animals will recover after a fairly severe disease, and they may not return to full health and production at the level they were before they became infected. The high mortality we associate with foot and mouth disease is due to the control methods that are typically used. The common method for control in a disease-free area is stamping out, and I'll come back to that. However, some strains of the virus, because there are many different strains, have higher mortality, and the mortality can be high in young animals also, more so in young animals than adult animals. It's very important to remember that this is not a public health or a food safety concern, but it's a major disease for livestock. So even though the animals recover, they go through a very painful, serious disease with severe lesions on the hoofs that makes them very lame until they recover, if they recover, and severe lesions in the mouth, which makes them unable or unwilling to eat. And FMD is very prevalent around the world. The World Organization for Animal Health, also known as the OIE, makes all of the international rules on trade in animals and animal products in order to control worldwide transmission of animal diseases. There are 178 member countries. Nearly all of the countries in the world belong to the OIE, including the United States, and all of those countries vote on the rules for animal trade related to animal diseases. 96 of the 178 member countries are endemic for foot and mouth disease. They have it, and they've never been free of FMD. The free areas are primarily North America, Europe, Australia, New Zealand. Some countries in South America have recently become free, and the whole continent is working toward freedom. 66 countries are free of FMD. 11 have free zones where part of the country is free, either with or without vaccination. And 5 countries that were free have recently suffered from a reemergence of FMD. And when FMD reemerges, there's an emergency response to try and stamp it out and return the country to freedom. The United States has actually had 9 outbreaks of foot and mouth disease. And those 9 outbreaks occurred between 1870 and 1929. So in a 60-year period, we had 9 outbreaks of foot and mouth disease. Some federal laws were put into place limiting the importation of livestock and animal products that could bring in the virus, and that has greatly helped to reduce the risk of FMD. So we haven't had a case in 85 years, which in my opinion is a small miracle that we haven't had a case since then, given the prevalence around the world. All of these 9 outbreaks are controlled by stop movement and stamping out. And this was at a period of time when there are no diagnostic tests. So it was all based on observation of clinical signs and rapidly killing animals that were affected and any animals in contact with affected animals. So this is how we used to respond to foot and mouth disease, but we can't respond that way anymore. The U.S. livestock industry have changed dramatically since 1929. The factors requiring a change in the planned response to FMD is we have very large herd sizes now, dairies with more than 5,000 lactating cows, feedlots with more than 50,000 animals on one site, sow farms with more than 20,000 sows. And you just can't kill all of those animals quickly enough to stop virus spread, and if you could, you couldn't dispose of the carcasses. And we have extensive movement of animals now. There are estimated to be 1 million pigs on the road each weekday in the U.S., and that could rapidly spread the disease. There's also public resistance to stamping out, because stamping out means you kill a lot of animals that are still healthy, and environmental concerns with carcass disposal. As we're experiencing now in Iowa with avian influenza, there are major problems with rapid disposal of large numbers of carcasses. And changes in the OIE policies related to FMD-free with vaccination. The World Organization has now changed the rules so that you can vaccinate and still be declared free of vaccination under certain circumstances. So what are the tools to control FMD? Because these tools have worked 9 times previously in the U.S. And this lists those tools. But if we have a large outbreak of FMD, those tools will be rapidly overwhelmed. We found out with PEDV in swine and avian influenza in poultry that the biosecurity we have in place for endemic diseases isn't adequate for highly infectious foreign animal disease. Stop movement will be initiated, but in some industries like the swine industry, if you stop movement, animals have nowhere to go and they have to be euthanized for welfare purposes. So you can't stop movement for very long. Stamping out, where you slaughter all clinically affected and in contact susceptible animals, preferably within 24 hours to stop virus spread. We simply can't do that in these large facilities. Trace back and trace forward. Where did the virus come from? Where did it go to? In a large outbreak, isn't the capacity to do all of the tracing. Rapid diagnostics, we're in much better shape than we were for rapid diagnostics, but that can be overwhelmed in a big outbreak. And vaccination is an extremely important tool, but the USDA acknowledges that we don't have enough vaccine even for a single livestock dense state if we have an outbreak. So for those reasons, the USDA, which is responsible for controlling outbreaks of foreign animal diseases, working with state animal health officials in the industry, has come up, working with academia, come up with the phases and types of an FMD outbreak, which would allow the decision makers to respond to the outbreak as it unfolds. Now, the decision makers will make decisions based on what's happening at the time. But this phases and types guideline helps everyone to think through how to respond in case the outbreak gets out of control very rapidly. During phase one, it's the first few days of the first case, there would be stop movement and stamping out until it becomes apparent the size of the outbreak. If it's a small focal outbreak with small numbers of animals, they will continue with stamping out. If it has been spread to a moderate regional area, they will perhaps continue stamping out and use vaccination to slow the spread. Anything larger than that, and we depend on vaccination to slow the spread or stop the outbreak. And as I mentioned, we currently don't have enough vaccine to help to slow the outbreak. So if it gets out of hand, it could spread to a type 5 catastrophic U.S. outbreak, and that could happen within days or weeks of the beginning of the outbreak if it spreads as fast as porcine epidemic diarrhea or avian influenza. At that point, probably the emergency response would be stopped or slowed down, and it would turn into a long-term control program to attempt to get rid of the virus. And we would have a lot of animals that get sick, and many of them would recover and become immune. So with that brief overview of emerging diseases, my conclusion is that the prospects of the emergence of new diseases is inevitable. It's inevitable that we will see the emergence of new human and animal diseases for a lot of the factors that were discussed. Human dependence on livestock, poultry, and aquatic animals for food and livelihood limits some of the policy options. If we have policy options that greatly limit the ability to produce food, then people in countries especially that are food insecure will become more food insecure. And protecting human and animal health and food production will be essential going forward. This is a statue of Dr. Norman Borlaug, the father of the green evolution. And this statue was recently installed in the U.S. Capitol. Each state is allowed to have two statues in the Capitol rotunda. And Iowa recently replaced a statue of a prominent politician from many years ago with Dr. Borlaug's statue. He's credited as being the father of the green revolution. In the 1940s, he developed disease-resistant high-yield wheat. In 1970, he was given the Nobel Peace Prize for his work with the Green Revolution. And then he established the World Food Prize, which is awarded every year to someone in the world who's had a great impact on food production. The Green Revolution, along with mechanized agriculture and fertilizers and irrigation, increased crop yields and prevented famine in India and China. He's credited with saving 1 billion people from starvation in those parts of the world. When he received the Nobel Peace Prize in 1970, Dr. Borlaug said, "The Green Revolution has won a temporary success in man's war against hunger, which could provide sufficient food for humankind through the end of the 20th century," which was 15 years ago. Unless the frightening power of human reproduction is curbed, the success of the Green Revolution will only be ephemeral. He also said that agricultural scientists have a moral obligation to warn the political, educational, and religious leaders about the magnitude and seriousness of the arable land, food, and and population problems that lie ahead. So what do we need to do to avoid and manage biological crises, emerging diseases? We need a one medicine, one world, one health approach to diseases. International collaboration led by international organizations funded by the developed world. We need to strengthen the public health infrastructure and veterinary services in all nations. We need government agency, private sector, and university collaboration to do this. We need to accelerate the application of modern science to improve diagnostics, vaccines, and antivirals, which means increased funding and streamlining some regulatory hurdles. And we need to encourage population control. And I don't have great ideas on how to do that. So that concludes the presentation, and I'd be happy to take some questions or hear some comments.
Thank you so much, Dr. Roth, for providing our audience with such a wealth of information. We will now open up the lines for the question and answer session, and also remember you can submit questions through the webinar system. Operator?
Thank you. At this time, we would like to begin the question and answer session of the conference. If you would like to ask a question, please press star then 1 and clearly record your name for question introduction. You must record your name clearly for your question to be introduced. Again, to ask a question, star 1 and clearly record your name. One moment, please, for our first question.
So, Dr. Roth, while we're waiting for our first question, you mentioned that the U.S. does not have a sufficient supply of FMD vaccine. So what's the situation with North America Foot-Mouth Disease Vaccine Bank?
So there is a vaccine bank shared by Canada, the U.S., and Mexico for foot and mouth disease. However, that vaccine bank was designed and initiated more than 20 years ago when the plan was we would only need limited amounts of vaccine to do ring vaccination around an outbreak while we proceeded with stamping out. So FMD vaccination is complex because there are more than 20 strains of the virus that you need to stockpile vaccines against, and they're not cross-protective. So the vaccine bank, as the USDA has stated, does not have enough vaccine for even a single livestock dense state. So there's a need to increase the amount of vaccine, and there's a recognition of that need, but the funding so far has not become available to do that.
Thank you for that response. Operator, do we have a question from the phone?
Yes, our first question comes from James Alexander. Your line is now open. Mr. Alexander, please check your mute button. Your line is now open.
Mr. Alexander?
I did not pose a question. I'm not sure how that happened.
Okay. Well, thank you anyway for participating.
You bet.
And at this time, I show no additional questions.
Well, let's continue some discussion, if we will, Dr. Roth. So, in relation to the current H5N2 avian influenza outbreak happening now, why isn't vaccine being used to control this situation?
So influenza vaccination in poultry, much like in pigs and people, is very complex. There are licensed avian influenza H5 vaccines, but they are based on the old strain or the previous strain of H5. They don't match the current H5. They may provide partial protection. And there are discussions about using that vaccine, especially potentially in turkeys. Concerns with using avian influenza vaccine, there are several concerns. One is that it can mask the presence of disease, so the birds don't get sick or don't get very sick, but they can still be infected. And with avian influenza, if they're infected, they still need to be destroyed because there's concern that that virus might mutate away from the vaccine and also mutate to become zoonotic. So with avian influenza, the disease does need to be eradicated. Vaccines may be a tool that they'll use, but that decision hasn't been made yet. It takes time also to change the vaccine to match the current strain. Also with vaccination, if we vaccinate, we lose all of our export markets for poultry and poultry products. And that would also be a long-term loss if we continue to vaccinate.
Okay, thank you for that response. Operator, I'll check with you to see if our audience has any questions for our presenter today.
Yes, I am showing that you have one question from Ms. Shantae Newton-Meyer. Your line is now open.
Hi, I know you talked a lot about vaccinations, but how have you seen, I guess, the benefits and, of course, the challenges with using, like, antibiotics?
So most of these diseases are viral diseases, so of course antibiotics don't apply to that. And there are a lot of issues around antibiotic resistance that we probably can't get into here. And because they're almost all viral, it probably doesn't apply.
Thank you, Dr. Roth. Operator, do we have any additional questions for our presenter?
Showing no additional questions at this time.
Well, Dr. Roth, I want to give you the opportunity if you have any points that you want to emphasize to our audience as we look at our food security and food animals.
No, I've had a great opportunity to present, my thoughts in that area. My email address is on the screen, and if people would like to email me with questions or comments, I'd be happy to receive them.
So, on behalf of COCA, I would like to thank everyone for joining us today with a special thank you to our presenter, Dr. Roth. We invite you to communicate with our presenter after the webinar. If you have additional questions for today's presenter, send us an email at coca@cdc.gov. Put May 28th COCA call in the subject line of your email, and we will ensure that your question is forwarded to the presenter for a response. Again, our email address is coca@cdc.gov. The recording of this call and the transcript will be posted to the COCA webpage at emergency.cdc.gov/COCA within the next few days. Free continuing education is available for this call. If you participated in today's COCA conference call and you want to receive continuing education, complete the online evaluation by June 29, 2015. Put in course code WC2286. If you're going to complete the evaluation between June 30th, 2015 and May 27th, 2016, use course code WD2286. All continuing education credits and contact hours for COCA conference calls are issued through TCE Online. It's the CDC Training and Continuing Education online system at www.cdc.gov/TCE Online. To receive information on upcoming COCA calls, subscribe to COCA by sending us an email, same email address, coca@cdc.gov, and write subscribe in the subject line. Also, we have a Facebook page for our health partners. Like our page at facebook.com CDC Health Partners Outreach to receive COCA updates. Thank you again for being a part of today's COCA webinar. Have a great day.
This concludes today's conference. All participants may disconnect at this time.